All right, hey, let's move on from arc length to surface area. And when they say surface area here, I should say they specifically mean surface area of one of those solids of rotation. Of a solid of rotation or revolution. Okay, so let's imagine you've got some sort of function here, this red function, and you're going to rotate it around the x-axis, and that's going to create a three-dimensional shape. And we already know how to find the volume of that thing. We did that a couple chapters ago. But let's talk now just about the surface area. Like if you needed to paint it, how much paint would it take? So I'm not very good at drawing these, so let's just steal some drawings from somewhere else. And so yeah, when you rotate this thing around the x-axis, it creates this sort of, I don't know, what would you call that, a vase of some sort, shape. And like before with arc length, we are just going to cut it up. Let's use red. We're just going to cut it up into little strips, little pieces. And we're going to look at one piece at a time, and we're just going to talk about the area of one of these strips of paper. I think about those construction paper chains I used to make when I was a kid, right? This is one link out of one of those chains. But really what we're going to imagine doing is we're going to cut this strip out of the shape. We're going to cut the circle open and lay it flat. And we're going to smush it out flat. Oops. And it looks something like this. Not a rectangle, more of a trapezoid, actually. But we still want to talk about the area of this. And then we can just eventually, add up all the areas. That's what integrals do for us. So again, this is not exactly the area of a rectangle. It's close, though. And as we get infinitely skinny, it'll get infinitely closer. So we really still are just looking at length times width or something like that. And let me talk about this part right here, which came from there. That's not just dx anymore. Because it's not parallel to the x-axis, right? It's on a slant. So it's not just a change in x, but rather it's a d... d arc length. It's a little change in arc length, right? So we'll use that instead of just x. So hold on to that for a second. But the other side is just the length, the circumference of this circle, right? Remember, we took a circle and we cut it open and laid it flat. So the circumference so that's the circumference of the circle. Circumference, we do know a formula for that, which is 2 pi r. R is this radius right here, the distance from here to here. And that distance, of course, is just the function value. It's y, or f of x, same thing. So you can call it y, or we can call it f of x. So the circumference will be like 2 pi y, or maybe a little bit more comfortably for us, 2 pi f of x. So let's talk about multiplying those two things together. What we want to add up is going to be a 2 pi f of x times a little bit of arc length, And the arc length we already know from last section, 1 plus f prime of x squared dx. Okay, I just kind of waved my hands a little bit through that geometry formula. I don't feel like I proved it with rigor. If you want to see it with a little more rigor, let me know. But for the moment, let's go ahead and just jump to the actual books, the actual official formula for arc length, right? And here it is. Sorry, not arc length, surface area. Official formula for surface area here. So we have, let's see, let's go back to blue. We essentially have that multiplication there. We've got arc length and we've got circumference. Those two things multiplied together. And I do just want to point out that, of course, there's a couple different versions of this based on whether your formula is in terms of x or whether your formula is in terms of y. And also based on which axis you're rotating around. So this is all set up to rotate around the x-axis. And really the only thing that really makes a difference there is what's radius when you think about your 2 pi radius, right? Because if you're rotating around the y-axis, your radius is a different thing. But we'll look at an example of each one of those. So let's go ahead and go do at least one example now. Maybe we'll save a couple more examples for the next video. Okay, so let's look at our first example. So let's determine the surface area of the solid obtained by rotating this particular function about the x-axis. Okay, so let's go ahead and start with a picture from -2 to 2. And in case you don't recognize this formula, you can certainly graph it, but it happens to be the equation of a circle of radius 3, or at least the top half of a circle of radius 3. So it looks like that. The circle, again, would go from -3 to 3. We're only finding the surface area, rotating it from -2 to 2. So -2 to 2. Oops, we're going to take that much of the circle. Going to rotate it around. So let's see if I can copy it down there. And then just sort of put a... Oops. We're getting like the shape of like a pitted olive or something, but we just want the surface area, what it would take to actually paint this thing. Okay, so let's go ahead and set up the formula. In case you don't remember, it's right there. So we need 2 pi radius times arc length. So the surface area will be the integral from -2 to 2 to pi radius, which is y, which is f of x, which is square root of 9 minus x squared, times arc length. Okay, so maybe I should have figured that out first, but here we need the square root of 1 plus the derivative of the function squared dx. You might remember from the last section that I said even arc length, the integrals can get bad pretty quickly. And this one is like integrating arc length plus some extra stuff. So you can imagine the integrals get bad even faster. And in the homework, there aren't too many problems just because there aren't too many that are really doable by hand. But let's see how far we can get with this one. So let's figure out if the original function is 9 minus x squared to the 1/2, then the derivative of the function, y prime or f prime, that needs to go in here, that is, in chain rule, 1/2, 9 minus x squared to the negative 1/2 times the derivative of what's inside, the negative 2x. We can clean that up a little bit. The 2 and the 2 cancel. 1/2 comes back down to the bottom. So we could say this is negative x over the square root of 9 minus x squared. Okay, so that's what needs to go in here. Negative x over the square root of 9 minus x squared. And for once, we're actually grateful for this squared right here, because it's going to knock out this square root. So let's see what we can do about simplifying this integral. Negative 2 to 2, 2 pi square root of 9 minus x squared. Inside the square root, the other square root, I've got 1 plus, so keep in mind when you square a fraction, you square the top and you square the bottom. So x squared over 9 minus x squared. I'm going to keep working algebraically with the stuff inside the square root. I'm just going to get a common denominator. So I'm going to replace 1. I'll just save some ink here. I'll replace 1 with 9 minus x squared with 9 minus x squared over 9 minus x squared. So that's the same thing as 1. Now we have a common denominator, so we can add those together. The stuff inside this square root. Let's see, the x squared, the top just becomes 9. The bottom becomes 9 minus x squared. And I'm actually going to separate this. You can separate square roots top and bottom, so square root of 9 square root of 9 minus x squared. And I'm actually starting to smile here because the rest of my integral that I didn't copy down, all this stuff, square root of 9 minus x squared, integral from negative 2 to 2. I'm going to move the 2 pi out front of the integral. It's a constant. You can factor that out. And finally, that and that. Oops, I left the dx off the end. Those cancel. The square root of 9 is 3. I'm running out of room, but fortunately we're almost done. So the integral now looks like 2 pi integral from negative 2 to 2 of 3 dx. The integral got super simple this time, which was nice. The fact that it's based on a sphere, and there's just a basic geometry formula for a sphere, is why this integral got so simple. But let's go ahead and finish the integration. So we'll get 2 pi times 3x, evaluated from negative 2 to 2. When we plug in 2, we get 6 times 2 pi, so we get 12 pi. And then when we plug in negative 2, we get negative 6. So we get minus another negative 12 pi. And the surface area of our pitted olive that we had up here is 24 pi. Oops, 24 pi. So we need exactly 24 pi square units of paint to paint the surface area of this thing. All right, we'll look at one more example in the next video.